double bass player and composer improviser, also working with digital and electronic sound.
Hello, I am Teresa Pelinski. I'm a PhD student at the Augmented Instruments Lab, but that's Professor Andrew McPherson's lab there. I'm also a student of Professor Rebecca Fiebring from University of the Arts London. And yeah, I'm finishing my third year, so I still have another one left. And this project, part of things I'm thinking about in my thesis. Yeah, so maybe we will start by giving a general idea of the project, of what's going on. I don't know if this is working or if it's needed. It's for the recording. Okay, then. So I just put it here. I thought we had to like.
Yeah, that's just for the video.
Okay. Yeah, so since there's not much time on the system we're using, I think it's better to just see it in a picture.
This one has a clip, otherwise, if you want to stick it.
Sorry, this was working like a second ago, and as usual, it's not working now.
Usually when it complains it.
Sorry. Source.
Well, maybe while Teresa
Just turn it off.
Turn it off whenever. It was there. I was turning it off. It's fine. Okay, there it is. Yeah, so maybe we'll wait. Yeah, so this is a system that involves Adam's FAAB, which is the feedback-actuated augmented bass, right?
feedback-actuated augmented bass.
Okay. I always miss the A's. Anyway, so that's it here. We put some piezos in it. These are the piezos that go to a cable. A piezo is basically a contact microphone, at least how we're using it. And yeah, so we're using some very basic AI models. And typically and maybe following on the conversation of mapping or whatever, here we're using AI models to kind of compress the information from these piezos. So there's eight piezos, and then we just pass them through this dimensionality reduction model. Dimensionality reduction, reducing dimensions, so we go from 8 to 4 signals, and that's why we're looking at like it as a bottleneck. And then the output, which is like this orange line here, goes to a modular synthesizer. And something we added here that I think is quite funny is that there's like a feedback loop, but like a digital. I mean, this is a feedback instrument, but then aside of that, we added like a sort of digital feedback loop here, in which like the output of the model also conditions the model itself. And how the model is conditioned is by the idea that there's not only one model, there's actually an ensemble of models. And this comes from some thinking about, in my PhD I was looking at tools and plugins that people use for integrating machine learning and AI in musical practice, as in like live performance. And I found that many of these tools were actually having some sort of like black box models. So the sort of design material when you were like building your performance was with these tools and in this like integrating these machine learning and AI algorithms. The design material was in the data. So what you modify and what you create is the data, not as much the models. You are not able to change the architecture of the models. You're not able to like change how they're trained. And I was interested to see, can we make the models materials? And yeah, that's actually how I ended up calling the system like ai-mami, as in models as materials interface. AI models as materials interface. So yeah, that's how that's the idea that there's like the output gets fed back into, the output basically gets fed back to like choose a model amongst a collection of models. So we're not only working with one model, but a collection, but only one sounds at the time. And the idea is that there's a space of models yeah, and we call that the hyperparameter space because all of the models are versions of the same model, they just have different hyperparameters. Hyperparameters are parameters that are not optimized in the training. These are parameters that you set initially, and since they're not optimized in the training, the only way you can know which ones were better is by training lots of models. So that's why we have so many models. And yeah, that's how that's like the theory of it, and then how we implemented this is with actually a Bella Pepper module. Yeah, anyway, maybe it's not that interesting, but yeah, it's running in a Pepper which is a Bella. It's running on a Bella computer integrated in a Pepper model, so we can interface with a modular stem. And that's the technical stuff, but I think that's not the most interesting. I think the actually interesting bit is the process of collaborating between us. Yeah. So yeah, maybe. Yeah.
Which this collaboration started really a month ago, I think, when Teresa arrived in Berlin, and we recorded a data set of fairly small data set of about what 40
minutes.
Yeah, 40 minutes.
Yeah.
Okay. So using this feedback base, and maybe I should just give a very brief explanation. It has a speaker built into the back, which causes the strings to go into self-resonance. And yeah, so we recorded these 40 minutes of not really a performance, but more me just like playing some of the things I was working on, and they were then recorded not by microphones, but by the 8 piezo transducers. So the FAAB, I don't know, I'll just turn down the model now. The FAAB in itself is the feedback base. That's sort of how it runs on its own, creating string feedback. There's also different kinds of signal processing possibilities. And so on and so on. I did 40 minutes of that, and then you started training various models, I think.
Yeah, it was basically the same architecture, but with, as said, different hyperparameters, so different number of layers, and yeah, basically number of layers. There's like a multi-head encoder, whatever. So parameters of how this model, it's like yeah, instances of the same model. And yeah, so we wanna actually. So we've been interested in like practice research, sort of like documenting the process, and I think a way of showing it is I have the versions of the code, so like the stages at which this system has been at. So we're going to demonstrate the stages of this the model until we arrive at the current state, which will be the one we will play in the performance. So yeah, first, so the idea is that this thing, right? Whoops, not that. Oops. So there's this model output, but this is outputting at like basically 22 kilohertz 50. So this happens too fast. We cannot like change models that fast because you would not be able to hear anything. So actually like configuring this sort of like digital feedback loop and making it work with Adam's instrument has been what's taken most of our time. So how to like, yeah, there's the idea of there's the conceptualization, but then there's actually like the making things work in practice and like playing with it. So the first version of the system we had changed models periodically. So it just looked at the output over a half a second, averaged that output and mapped to a point in the hyperparameter space. Basically every half of a second you would get like either staying in the same model or changing. And this is how it sounded. Whoop, not that. Yeah, so, yeah. Sorry, go on.
Yeah, I mean, it was basically, it felt like there was very little, it didn't make a great deal of difference what I actually did. The models were like scrambling around. on their own and changing very quickly.
Yeah, so the idea was here that we were trying to navigate this hyperparameter space where the models are at. And like initially I had this idea that, oh, there's going to be this sweet, smooth trajectory and it's going to sound very smooth, but then you implemented it and it sounds like this. And I was really annoyed as in like, how do we do this? Do we like change the gains, like sort of like stretch the space in some dimensions so that like it looks smoother, so that it's more playable? So we added some gain parameters to this, kind of could like did something, but like it was still like, a point I think that was interesting is that like whilst my initial interest with this was that the meaning was in the models itself, as in like you could hear the models and their different characters. Here, since there was this like sort of like imposed periodicity, it's like the meaning was in how the models were changing. That made sense. It's like as if the signals did not matter that much, but it was like how they were changing. And the idea was that you could hear something in the models. So the second iteration of this, we started working with ratios of like basically the standard deviation of the signals, how like they were varying with respect to the volume in the instrument, and that's basically how it's the state at which it is now. I don't know if you want to say something about like playing with the ratios.
Playing with the ratios.
As in like when like the Smith trigger, when we added like the Smith trigger, it's basically what's up now.
Yeah, with these like sort of more adaptive parameters, I think maybe we should just like show what it sounds like now.
Sorry.
So at least here, it feels like the system has gotten a lot more responsive. And also, for example, when are we up? Time's up.
We can wrap up.
Okay.
It's time for wrapping up.
Yes.
Okay. Yeah, we had some notes about, like the analysis between how we use things that Adam knows from working with feedback instruments to tune a digital feedback system. So I think it was interesting, but yeah, I think, and also some ideas about like cybernetics and machine learning, but yeah, we can talk about it later. Yeah, thank you.
Thank you.